Yo, what's up? Welcome back to my game engine series, where I tried to make a game engine in C++ and Vulkan, from scratch. In the last video, I realized I didn't actually explain what I'm actually making. I'm making a game engine, of course, but what does that actually mean for this series? I'm not trying to remake Unity or Unreal, because to me that seems rather pointless. I'm trying to make a piece of tech that makes the games I want to make. But what does that actually mean though? So when it comes to game engines, there are two major categories that game engines fall into in the modern day. Generalized and specialized game engines. A general game engine is what people think of when they think of a game engine. These are tools like Unity, Godot, Unreal, GameMaker Studios, and RPG Maker. These are general purpose game engines that allow users for the most part to make any type of game they want, with only the constraints typically being either they have to be 2D or 3D, with the exception of voxel games, like Minecraft. Specialized game engines are game engines that typically run either just one game or a group of similar games, such as League of Legends, Minecraft, and Factorio. Each of these games have a game engine underneath the game. These engines will be very different from each other, and what's possible to do in one won't be possible to do what's in the other. These game engines are designed around the game's needs rather than the other way around, unlike general game engines. When it comes to indie game development, this is typically what people are making when they are making a game engine. That being said, there are indies out there who are making general game engines. It's just a lot rarer. For this reason, I likely won't ever be releasing the game engine for other people to use, because I'll only be using it for my games. This gives me a huge advantage which I'll leverage. When you're making a general game engine, you have to design the technology around the fact that anyone can make any type of game either in 2D or 3D. This all means that I can do things that you can't get away with when making a general game engine. So for example, when it comes to entities, such as enemies, items, and other things, I don't really need an entity component system to handle these, because I can hard code all the entities, because I know all the entities that I want to put in the game. In theory, I could use a text editor such as Notepad as a level editor, by simply just adding all the initial positions of all the entities and other things I want to add to the game in a big giant text file. That's something I likely won't be doing though. In short, I just have to add the features that I need for the game that I'm making. And that's what I'm making. I'm making a specialized game engine that's going to make the games that I want to make in the future. So, what have I been up to? To get to the next stage of game engine development, I have to fix a major issue that's been plaguing the engine. And this is all to do with materials. Such as diffuse and metallic materials, they were typically represented by one texture and one sampler. This is a problem. The problem being that different models have different numbers of textures to represent each material they contain. So materials such as diffuse materials and metallic materials might actually have more than one texture. To get around this in the old version of the renderer, I would have to write multiple shaders and make multiple graphics pipelines to support materials with a different number of textures. This, of course, is not scalable at all. To fix this, I had to add support for bindless textures. And if I have bindless textures, I also need the ability to update graphics pipelines and cache the result once the graphics pipeline has been created. Having bindless materials means that I have an array of resources that I can access via index. Despite the name, we are still actually binding these resources for the material that we are going to use. But this means we can have any number of textures and samplers for a given material. The descriptor sets now need to be able to update themselves with data after they have been bound to make this possible. This requires a rework of the descriptor pool, which now allows descriptor sets that come from that descriptor pool to be updated after they are bound. These descriptor sets can even be updated with dummy stand-in textures and samplers. Once this was completed, for these descriptor sets, I could then index through an array for a given material inside the shader at runtime. Unfortunately, this is only half the puzzle complete. We still need to fix graphics pipeline generation. Vulkan is very different from other graphics APIs, like OpenGL. With OpenGL, you typically have GLSL shaders in text format, and you send that over to the GPU to be compiled into a program. With Vulkan, you first compile the shaders into an intermediate representation file format called an SPIRV file. This file is then passed to the graphics driver, compiled, and turned into instructions that will run on the GPU. We can actually take advantage of our compile shaders. By decompiling the spirv file, we can actually see the GPU instructions that are going to be sent to the graphics driver. We can then use this data to generate the graphics Vulkan pipeline. So if I compile the vertex shader with this command, and then decompile the spirv file we just compiled with this command, we get this text file. If I open up this file, you can see that it has a lot of instructions in. These instructions will help us support any given material. So the next step is to parse the file. So in the graphics pipeline, for example, I can set up a transparent material that has back face and front face culling. With the parsed data, we also work out how many descriptor sets we need. By finding the uniform opcode in the parsed data, we can also create the descriptor set layouts. Additionally, while parsing this code, we create binding entries and store the values for each binding. And finally, we get out the resource type for each binding. Descriptors in Vulkan are something else, man. If you want to learn more about Vulkan descriptors, I'll link a video in the description that explains things really well. I always return to this video to refresh myself on the ideas and the basic concepts of descriptors. Vulkan actually provides a parser for this task, although I've written my own smaller version of the parser to really help get my head around what's going on. I'll eventually replace my version with the Vulkan version, once I need a more robust parser. This is actually all the work you need to do to have bindless materials. However, there's a problem. Pipeline generation of Vulkan is quite expensive, and if we have to do it again and again and again for each material, things are going to add up, and loading time is going to get excessive. So we need to speed up graphics pipeline generation. This is where caching comes in. Vulkan actually already supports this by having a lot of functions that help read and write binary files for caching graphics pipelines. The first thing we need to do is look for a cached pipeline file. If one doesn't exist, this is the first time we're actually generating a graphics pipeline, and there's nothing we can do to speed this up with caching. So when we finish generating the graphics pipeline from scratch, we then save the results out to a binary file. For subsequent runs through creating graphics pipelines, we pick up the cached file and only modify the parts for a given material. So what does this mean for a current engine? Well, as you might have already guessed, we have transparency support, which is cool. We also now have the ability to deal with materials that come with a different number of textures for a given model. So for transparency, if I take you over to these chains and the ivy, all these parts of the model have transparency, and they are being culled depending on which way we face. So both sides of the transparency are being respected. So if I take you to one side, and then the other, you'll see that things are being rendered correctly. We actually need to order the transparency back to front. So if I take you to this model where I haven't ordered them, you'll see that there are some weird artifacts. I haven't quite cracked translucent materials yet, which is pretty clear in this chess model. The heads of these pawns are meant to be translucent. But if I look from above, you can see that they're transparent. And if I look from below, you can see that they're completely opaque. I believe this is because two different materials are fighting each other, rather than working together. This is something I hope to fix in the future. I've actually been using this chess set model to test out potential ways to place 3D models in a scene to create a level. In this GLTF model, each piece, pawn body, and top are completely separate from each other. I've worked pretty hard and tested quite a lot to make sure these models are placed in the correct place on the chessboard, as it's a good starting point for a 3D level, as it's incredibly obvious if a piece is in the wrong place. I'm doing this by looping through the hierarchy of scale, position, and orientation data for each child model, building up a local matrix stack, and then I multiply them all together for each model, giving me the correct orientation, scale, and position for each submodel in this model. This is only limited to one model that has multiple models inside it. I hope though in the future I can use this technique to do this for multiple models that have nothing to do with each other, and consequently creating a level. Additionally, I've added music and sound effects to the engine. I've used the SDL mixer library to help with this. So if I press the number 1 key, you hear a sound effect. And if I press the number 2 key, you'll get music that loops. Let's stop that for now. Shout out to anyone who knows where that's from. I was actually thinking about writing my own parser for WAV files instead of using a library. The problem here though is if I try to write everything myself, progress will get slower and slower over time. I'll need to support more features that libraries like SDL Mixer already support. So I decided because I'm using SDL anyway, I might as well just use SDL Mixer as well. I've also made a small lighting improvement to the fragment shader. Now with this light source over here, you can see that things get darker as you move further away from the light source. We can also adjust the intensity of this light source and the range of the light, meaning that we can get different lighting effects from this particular light source. This light source is only really here to demo things like physically based rendering. Further work is going to be needed to make lighting more efficient and useful for multiple lights. All the progress I've made has been great, but it's been a huge struggle to get this far. Progress has been slower than I would have liked. I'm still very dissatisfied where the engine is currently. One major issue right now with the engine is the fact that it only really works with one model. I also want to show you this model. As you can see with this model, things are beyond broken. But this is the same code that renders the other models completely fine. For some reason this model's scaling is completely off. Things are too small or way too big. I haven't yet found out why this is happening, which is pretty frustrating. I know some people who saw the last video are also learning Vulkan and are making their own game engines. I think it would be disingenuous to them, and those people who aren't making their own game engine, to only show things that are going right. Because no matter who you are, or how you're going about it, making your own game engine and using Vulkan is difficult. Although you can see this model is completely broken, believe it or not, the engine is in a much better state. As when I started making this video, every other model that I loaded into this engine didn't work at all. I mean, nothing rendered. And when it comes to rendering, this is the most frustrating error you can get. That being said, I managed to talk to a 3D artist about this problem. And he told me that free models online might not be the highest quality. This was actually really eye-opening. He also taught me some basic diagnostic techniques that I can use in Blender, all to make sure that the models are at least functional. And even though I'm just a programmer right now, I'm likely going to have to get quite familiar with Blender if my game's going to be in 3D. Even though it's a small first step to learning Blender, I think it's a good first step. And this is the advantage of making a specialized game engine. I don't have to get every single type of model working in my engine. I can exclude models that would be really difficult to render correctly. I'll provide links below to all the models I've used in the description. So that's where I'm currently up to. There is so much more work to do even with just the renderer. And believe it or not, it's still currently too slow. I'm only testing things with one model. Eventually there are going to be many models in the scene, with a lot of different materials. It's something in the future I hope to fix. Additionally, when it comes to Vulkan, there is another issue. If a computer has two different GPUs from two different manufacturers, it fails to pick a GPU to render from, causing a crash. But I guess I can't be too hard on myself. I'm only working on this engine part-time. Anyway, that's all from me. Thanks for watching. See ya.